First, any questions? Yes?
What's the class schedule for next week?
Well, I guess.
Are you going to be here on Wednesday night?
Yeah.
Okay.
But I'll understand it if, you know, it's just you and me.
It will be not me and you, I guess.
Oh, it would be not you?
Yes.
Well, I mean, if everybody's canceling, then I'll cancel too.
Or you could just cancel the class and then everyone would automatically cancel.
Are we talking about next week on Wednesday?
Yes.
Could we please have it off? I have like a zillion things I have to make.
You have to cook, is that what?
Yeah.
Well, I don't know. I don't think I'm at liberty to cancel.
You're in charge. You can do whatever you want.
You could do a Skype lecture. We can all Skype in, and then we could listen to you, and I could be cooking while you're lecturing.
All right. I don't know. I'll think about it, and we can talk about it on Monday if any of you deign to come. All right. So we were talking about some applications of QED, and we were looking at some of the simpler applications, and in particular we were thinking of a process called E plus E minus goes to mu plus mu minus, which of course is quite an interesting process, and in fact processes like this, as you raise the energy of the, if you have a colliding beam situation, as they did eventually at SLAC, they had E plus E minus colliding beams, and were then, as they jacked up the energy, were able to produce various all sorts of particles, typically pairs of particles, and they eventually, well then they would measure the total cross-section, and in particular they, the thing that they reported quite often was the ratio of the total cross-section to the total cross-section that we're calculating now, namely E plus E minus goes to mu plus mu minus. And this showed a bump each time it was possible to create pairs of quark, anti-quark pairs. And of course there was a bump for U, a bump for D, although you couldn't see the difference between them. But then there was a bump for the strange quark, bump for the charm quark, and so forth. I guess they even saw a bump for the B quark, BB bar pairs. I think they had an energy for that. And so, of course, the great advantage of the SLAC experiments was that the initial beam was electrons and positrons, and they understood what the electrons and positrons were. In more recent experiments, at higher energies, the initial beam is a proton, and the other beam is either another proton or an antiproton. And so you're shooting an enigma into a puzzle, and it's very hard to analyze what you get out. But they did find the Higgs at the LHC, so that's something. Now let me find where we were at the end. The picture, of course, is E minus, E plus. I mean, this is the Feynman diagram. mu minus mu plus. And we have been using a certain identity, and this identity, this was one of the homework problems. If you want, I'll go through the derivation of that homework problem, but let me just tell you what the answer is. Gamma A, gamma B, gamma C, gamma D the trace of these is gamma A to AD, A to BC, minus 4 A to AC, A to BD, plus 4 A to AP, A to CD. Okay, so this was a homework problem. I've sent you the solutions. I guess you don't need to have me do this in class. I'll tell you though what the basic, well, let me do one step of it. What you do is you just take gamma A, gamma B, and use the fact that gamma A, gamma B plus gamma B, gamma A is 2 A to AB. And so you rewrite this as minus gamma B, gamma A plus 2 A to AB. And then you have gamma C, gamma D. I don't know about you, but I find that when we have Roman letters, rather than all Greek, somehow it's easier to understand. Do you guys have that? Do you feel that way also, or you're Chinese, so everything is crazy? But the rest of you, do you? Doesn't matter to you. I once sent Weinberg an email telling him that he had too many Greek letters. I don't think he replied. Okay, well, if you apply this to the point we got in the calculation, and I don't think I should review all of that, except that, well, let's see, is there? No, I don't see any point. So what we get is we wound up with something like this. We had a trace of P3 slash plus mu gamma alpha P4 slash minus mu gamma beta. So this was one trace that came up when we summed over final spins and averaged over initial spins. And you see that this is P3, P4 times a trace of 4 gamma matrices. So it's P3C, P4D. Well, it's actually lower C and lower D. So let me just do that. Trace of gamma C, gamma alpha, gamma D, gamma beta. I guess that's the worst of both worlds, mixing them. Minus mu squared trace gamma alpha, gamma beta. Trace of an odd number of gamma matrices is 0, so we don't have to worry about that. About the one that's 1 gamma or 3 gammas. And if we now apply this formula, which has a bunch of etas in it, what we find is that this is P4 times P3 alpha, P4 beta, plus P4 beta, P3 alpha, minus P3 C, P4C, eta alpha beta, minus 4 and mu squared eta alpha beta. Okay, so that's what that is. And so then 1/4 the sum over spins of the amplitude squared is then 4 e to the 4th over s squared. Remember, s is p1 plus p2 squared, where p1 and p2 are 4 momenta. And so this thing is p1 alpha, p2 beta, plus p2 alpha, p1 beta, minus P1, P2, I'm just going to write it this way, plus ME squared times eta alpha beta, so it's this times P3 alpha P4 beta plus P4 alpha P3 beta minus P3 P4 plus mu squared and then eta alpha beta. Okay. So when you multiply that out, it simplifies somewhat, and you get 8 e to the 4th over s squared, and then you have P1, P3, this is Lorentz product, P2, P4, plus P1, P4, P2, P3, so maybe I should put some parentheses in there, plus mu squared P1, P2, plus me squared P3, P4, plus 2 me squared mu squared. Okay. And now you can simplify this using various, using the Mandelstam variables. S, of course, is P1 plus P2 squared, and this is the same thing by momentum conservation. This is P3 plus P4 squared, to the 4th power. That would be interesting, is it? And this is then 2me squared plus 2p1 p2, which is also 2mu squared plus 2p3 p4. So we get these two very different forms according to whether we expand with 1, 2, or with 3, 4, but it's the same number, same answer. And T, of course, is P1 minus P3 squared, and that's the same thing as P4 minus P2 squared, and, or minus that if you want, and that's equal to me squared plus mu squared minus 2p1 p3, and or it's the same thing, minus 2 p2 p4. Okay, so there are these various formulas, and these aren't, well, it's important to get them straight, of course, but on the other hand, there's not a great deal of meaning here. So, okay, so we have all these relations, and if you use them, don't make any mistakes, you can show that this expression here, the sum over spins divided by 4 of the amplitude is 2e to the 4th over s squared. And it has this remarkably simple formula in terms of the Mandelstam variables. P squared plus u squared plus 4s me squared plus m mu squared minus 2 me squared plus mu squared squared. So when you see an expression like that, you know you've got something that's relativistically invariant, because all these Mandelstam variables are Lorentz invariant. Now d sigma d omega in the center of mass, or center of momentum. 64 pi squared, 1 over E center of mass squared, ratio of final to initial momenta, and these things make sense since it's E plus E minus, mu plus mu minus, m squared, and the m squared is up there. And now there are a couple of things we can keep in mind. 4e squared is E center of mass squared is S, and all right, so let me switch notes now. So one can re-express this using this as a question. E to the fourth over 32 pi squared, E squared center of mass, S squared, P over K, and maybe I should have said which one was K. K is the electron one. Square root of E squared minus ME squared, and P is the square root of E squared minus MU squared. So K is bigger than P. And what we've got is this times that. And then I'm just going to write this bracket because it's just a repeat of that bracket. And if it's, I don't know if it's really worth doing, but you can rewrite this as alpha squared over 16 e to the 6th p over k. And now what you've got is e to the 4th plus k dot p squared plus e squared me squared plus mu squared. Okay. Alpha here, of course, is the fine structure constant. Alpha is equal to e squared over 4 pi. And for those who like putting in the salt and pepper of h bar and c, we get h bar c in there. And I should mention, I guess, that I may have mentioned this already, but anyway, E center of mass squared is 4E squared is S. So E is the energy of the incident electron or incident positron, again, in the center of mass system. All right, so now this K dot P, of course, is, this thing is length of K, length of P, times cosine of the scattering angle. And they're very, well, if you do that, what does one have? One has everything, well, all you do is replace this as by K squared, P squared, cosine squared theta, so that I don't think I need to rewrite the whole thing. If you take the limit in which the electron mass goes to 0, things simplify somewhat. And in the limit at E squared goes to 0, K is just equal to E. And in fact, in that limit, you have d sigma d omega, again, center of mass. This is ME going to 0, we get alpha squared over 4 E center of mass squared root 1 minus mu squared over E squared, and then 1 plus mu squared. This is, I'm following Schwartz very closely here, so there's no real need to take notes. Okay, so this is the expression, and now if you let the energy go so high that mu can be neglected, then obviously you just cross this out, you cross that out, you cross that out, and you get a very simple expression, alpha squared over 4 E center mass squared times 1 plus cosine squared theta. And if you integrate that, this gives you integrate this over d omega, you get 4 pi. You integrate this, it's the integral effectively from, it's 2 pi for the d phi integration, and then the d theta integration is x squared dx from -1 to +1, and so this is 2/3, so it's 4/3. So you have 4 pi over 3 plus 4 pi, and so that's, well, sigma finally is then 4 over 3 pi alpha squared over E center mass squared. So the 1/3 comes from there. Okay, so that is E plus E minus goes to mu plus mu minus. Now, this is something that, as I said, it's a very important cross-section. It was a fairly easy cross-section, though, because there was only one possible vertex here. One thing I guess that I forgot to, I think I forgot to mention this to you. In the calculation here, this Li is E psi bar E A slash psi E plus E psi bar mu A slash psi mu. So I think I might have just forgotten to write one down, but it's this thing that goes up there in the e to the time-ordered product of e to the I interaction with Lagrange and d4x. Any questions? I have to pay the TA. Hold on. Whoa!
Is that a Compton scatter? Is that the same?
No. You know, I hate all these names. I mean, when you can call something E plus E minus goes to mu plus mu minus, that tells you what the process is. If you then give it a name, you know, what does that tell you? That tells you that somebody was famous, but you don't remember who he was or what he did.
Oh.
So, and I, in fact, don't know the names of any of these things, although I know Compton scattering is gamma E goes to gamma E.
I mean, that expression looks like the Compton scatter.
Well, I'm not denying that there might be some similarity in cross sections, okay? And but we'll do Compton scattering later. What I want to shift to now is something that I don't know. Schwartz must have spent time in Slack. I'm obsessed with some of these. I shouldn't say. Oh, scratch that. Luckily, no one's listening. It's just us. Okay.
And the internet once you put it on YouTube.
What we're going to do now is consider a similar process, but instead it's going to be electron-muon scattering. And this is also quite a simple process to analyze. And again, the Li will be the same. It will be E psi bar A slash psi for the electron plus E psi bar A slash psi for the muons. And But this process, you see, physically, it's almost the same as electron scattering off protons. The difference is that the proton has a positive charge, but the charge winds up getting squared anyway, so it doesn't make any difference to lowest order at least. And so Schwartz discusses both processes together, so we can also think of E plus E minus, and then we can imagine that a proton goes across. And if we did, then we would have psi bar proton A slash psi proton with an E, or perhaps a minus E, just to indicate the proton had a different charge. There's the Rutherford, now of course, the celebrated thing is Rutherford scattering, and Rutherford computed E minus P plus goes to E minus P plus, and he got D sigma D omega as he was talking non-relativistically, ME squared E to the fourth over 4, P squared sine to the fourth of theta over 2. This is closely related to what you get in the Born approximation, or the first Born approximation in quantum mechanics, which is ME squared over 4 pi squared. The Fourier transform of the potential, let me put it in an absolute value because I really am a little spooked by a Fourier transform without an absolute value sign if we're doing a cross-section, but I think the thing is real. So this is ME squared over 4 pi squared, and then integral d cubed x, e to the minus I k dot x, e squared over 4 pi x, and this gives us ME squared over 4 pi squared, e squared over k vector squared, which is, well, it's a slightly different expression. It's ME squared e to the fourth over 64 pi, I'm getting 64 pi to the 4. I may have, maybe a typo, or I sine to the 4th theta over 2. A whole lot of pi's there. Am I, let's see, did I miscount? I was copying this from Schwartz. Let me just see if I perhaps got this. There's one. No? Well, I don't know. I'm just going to... Schwartz had this, so maybe a typo. I didn't check it numerically, so, or analytically. In any event, this is also similar to what Schwartz got earlier in scalar QED, and so anyway, I don't think we need to go through all these details. Let's now return to this calculation, electron-muon scattering, and what will the process be? Well, in Schwartz's notation, we're computing IM, and I'm thinking of this as 3, 4, S matrix 1, 2, and here this is 1, 2, 3, 4. And so this is going to be vacuum A3, A4, time ordered product, e to the I integral Li, P4th x, A1 dagger, A2 dagger, 0, and then product square root of twice the energies for each of the incoming and outgoing particles. By the way, these things are fermions, so whether you write A3, A4, or A4, A3 gives you a minus sign. On the other hand, an overall sign doesn't matter, and so we don't need to really keep track of whether it's A3, A4, and A1, A2, and so forth. Those all give us an overall sign, and we can just arrange the order as whatever it is. It gives us a plus sign, so we don't have to worry about that kind of a minus sign. Relative minus signs, on the other hand, are important, but they don't occur here. Okay, so this thing is going to be then 0, A3, A4, time ordered product, e to the I integral, or e to the I e integral, and will be psi bar e a slash psi e plus psi bar mu a slash psi mu d fourth x a1 dagger a2 dagger 0 square root to the product of them. All right. Now, when we expand that, of course, we have to take it to second order, and so what we get is IE squared over 2, 0. So I'm going through the steps again so that, I mean, Schwartz just writes the thing down. What will happen, by the way, if you ever have to do these for a living, after you do 2 or 3 or 4 or 5 or 10, it doesn't matter, it's not that much work. Examples, doing them my way from first principles, you will know, you will have so much experience and dexterity that you'll just write down the Feynman diagram, and then you'll write down the amplitude the way Schwartz does. But I think it's good to go through it anyway, when we're just learning. All right, so this is integral d4 x, d4 y, and what we would have here would be psi e bar a slash psi e plus psi bar mu a slash psi mu, and let's say that's all at x, and then it's times the same thing, psi bar e a slash psi e plus psi bar mu a slash psi mu, all at y, and this is all inside our time ordered product, and then we have A1, A2, vacuum product square root 2e. All right. Okay, so what do we do? Well, we need to choose which vertex to do what at, and what I chose was x to be the place where the electron gets stopped, and y to be the place where the muon gets stopped. And the other alternative is to switch them, and of course if you switch them, then you get the same answer, and so we can get rid of the factor of 2. And so what we get now is minus e squared over 2, no, this 2 is gone, minus e squared 0, A3, A4, integral d4 x, d4 y. And now, for the y part, all we need is the mu part. So we have psi, and I switched them around. Obviously that doesn't matter. Anyway, so this is psi bar mu a slash psi mu, and this is all at y. And then at x, what happens? Well, one electron is stopped and another one is started, and so, well, actually, the way I did it was a little, I'm somehow getting, you know, I need to follow my notes, otherwise you get hold up. So what I did here was I'm stopping this muon at y, and so this is e to the minus I p2y u of p2. And then we have psi bar e of x a slash, and so this is also at y, and so is a. E to the minus I p1x u of p1 0, and now we have product square root of 2e, but the 2e's are just the final 2e's. Everything else has gone away. The 2 pi q in the denominator of the expression for the fermion field is canceled because the a dagger a has a 2 pi cubed and a delta function momentum. Does anyone want to see this in a little more detail, or is this okay? Okay, well, you can see that what's going to happen now is that this one is going to start the outgoing muon at y, and this one is going to start the outgoing electron at x, and these things will be absorbed, these will be absorbed, and so what we get at this point is minus e squared integral d fourth x d fourth y u bar. In fact, just to make the notation a little more compact, I'm just going to say u bar 4, which means p4, s4, and so forth. Gamma mu, because this is gamma mu a mu, and actually it's this up here. So u bar for gamma mu u2, and then that will be altogether e to the y p4 minus p2, and then we'll have u bar 3 gamma nu u1 e to the I x p3 minus p1, and then we'll have vacuum time ordered product, and it will be a mu at y, a nu of x, 0, the e's are all gone. I think that's actually everything. Well, of course, this term here is just the photon propagator, and so what we have then is that this is equal to, in fact, I can call this I actually. It's minus e squared d fourth x, d fourth y, d fourth k over 2 pi to the 4th. So u bar 4, gamma mu u2, u bar 3, gamma nu u1, e to the iy, p4 minus p2, plus ix, p3 minus p1, plus ik, x minus y, and then down here we have a minus I over k squared. The I epsilon doesn't matter. We have a to mu nu minus 1 minus c k nu over k squared. Well, I wrote down the general gauge term, but of course, you know, the next thing I'm going to say is that the gauge term doesn't matter. It cancels. It cancels because the spinors are online. So in other words, well, we can't cancel it yet because we're integrating over k. But as soon as we do the d4th x and d4th y integrations, what we get this will be IE squared. Each of these will give us 2 pi to the 4th, 4-dimensional delta function. And what we get then is 2 pi to the 4th delta function of the sum of all the incoming and outgoing momenta. And then if you look, for example, at the x integration, this tells you that k is equal to P1 minus P3. And of course, you could see that from this picture here. If this is P1 and this is P3, then K here has to be P1 minus P3. And so what we have here then is U bar 4 gamma mu U2, U bar 3 gamma. This thing gives us gamma mu U1, and it's over P1 minus P3 squared, because that's what K is. But now if you took these things seriously and you let K mu be P1 mu minus P3 mu, and then that would occur in here, and then because of the Dirac equation of momentum space, this would cancel it, be m minus m essentially. Okay, so this is our amplitude, and this is I am Matthew Schwartz. So if we cancel the I, we have m is equal to e squared. This is t, e squared over t. Well, I say it's Im. I've got the overall 2 pi to the 4th delta function, which Schwartz put somewhere else. So let's just switching now to completely Schwartz lingo. We've got gamma u bar 3 gamma mu u1, u bar 4 gamma mu u2. Okay. All right. Well, now you have the nightmare of the gamma matrices, and real nightmare if you actually had polarized initial states and were measuring the polarization of the final states. On the other hand, you know, these are only 4x4 matrices and complex 4 vectors. A modern laptop could do this stuff in, you know, a microsecond or less. So this is not a big deal. And in fact, one of the famous Dutch theorists actually wrote a program to do all sorts of Feynman diagrams. I forget what he called it. The theorist is Veltman, who shared the Nobel Prize with Hooft several years ago for showing that non-engaged theory with spontaneous symmetry breaking was still really normalizable and in a gauge invariant way and so forth. I heard a story, by the way, it might be story time, that the difference between the way in which the two of them behaved before the King of Sweden receiving the Nobel Prize. With Hooft being younger, Veltman was Hoof's PhD advisor, and as Hooft took a deep bow before the king, and whereas Veltman simply nodded. And what that meant, I don't know. It may be that Veltman had back trouble, or maybe he was saying something too late. In any event, 1/4 sum over spins, amplitude squared in this sense, well, it's very similar to what we had before. It's e to the 4th over 4t squared, trace of P1 slash plus ME gamma nu P3 slash plus ME gamma mu, and now times trace of P4 slash plus mu gamma mu P2 slash plus mu gamma nu. Okay. Now, you may, if you remember, and it's still on the board up front, for E plus E minus goes to mu plus mu minus, we had two antiparticles. And consequently, two of these masses came in with a minus sign. And that's the principle, one of the differences between the two amplitudes. Otherwise, this is very much like, it's like E plus E minus goes to mu plus mu minus. And in fact, there's something called crossing symmetry, which if you go through it and work it out, you're able to actually formulate rules which take you from, which relate, for example, we are doing E minus mu minus goes to E minus mu minus. And you see, this is sort of the same in this. The reason it's called crossing symmetry is if you take this particle and switch it to the other side, it becomes an antiparticle. And similarly, this guy comes through and becomes an antiparticle. And so these two things are related by crossing symmetry. And it's actually a rigorous symmetry. And so Schwartz goes on and explains why this is, in fact, an example of this, of crossing symmetry. And if we have here P1, P2, P3, P4, under this crossing symmetry, what happens is P2 goes to minus P3, and P3 goes to P4, and P4 goes to P2. And one has also S going to T, T going to U, U going to S. And just, let's see, I could write this down again, or equivalently, we could just flash to the front of the front board and see, yeah, I guess it would be, well, I'm trying to find the exactly analogous expression, but unfortunately, it's not exactly analogous. All right, so I'll just write down the other expression. So this is the expression for E minus mu minus goes to E minus mu minus. If instead we're talking about 1/4 sum over spin m squared, and now for E plus E minus goes to mu plus mu minus, then this is e to the 4th over 4s squared. So you see s goes to t if you go from one to the other, or t goes to, I guess, anyway, the other expression was e to the 4th over 4s squared, trace of P1 slash plus ME gamma nu P2 slash minus ME gamma mu times trace of P3 slash plus MU gamma mu P4 slash minus MU gamma nu. So you see, because there are antiparticles in this expression, two of the masses come in with negative signs. And so if we had gone through a detailed analysis of crossing symmetry, we could have computed one of these and written down the other. But it's easier just to, and probably more informative, to keep this from scratch. In any event, going on with this expression, or actually using crossing symmetry. In other words, we already we had the expression for E plus E minus goes to U plus mu minus in terms of the Mandelstam variables. If we now write it in terms of the now write E minus mu minus goes to E minus mu minus in terms of Mandelstam variables, we get this. 2e to the 4th over t squared, and so that's this thing, and so that this again is E minus mu minus goes to E minus mu minus. M goes to M, let us say. And this turns out to be U squared plus S squared plus 4t ME squared plus MU squared minus 2 ME squared plus MU squared. Okay, so that's the hard part of the cross section. The rest of it is just the density of final states. Now, this was for electron-muon scattering. We can use this to discuss electron-proton scattering, and all we have to do is replace the mass of the muon with the mass of the proton. And so that's 105 MeV goes to 938, say, MeV. So it's a factor of 9, essentially. And Schwartz presents us with various limits of this. One of them is we send mu into MP, and then we send MP to infinity. And so this is a situation in which the center mass frame and the lab frame are the same because the proton doesn't recoil, or to put it differently, for the proton momentum to be the same as the electron momentum, the proton has to just sort of bare its teeth and look at the electron, and then it has the same momentum, 3 momentum. So the lab and the center mass frames are the same. P1 here is E, and we'll call it Pi. P2 is M proton and 0. P3 is E, P final of the electron, and P4 is MP0. So if you substitute these things in, everything, many things simplify, and you have Pi dot Pf is P squared cosine theta, and you can call that VE, V squared E squared cosine, this can't be right. Yeah, apparently it is cosine squared theta. And V here is P over E of the electron, and that's square root of 1 minus ME squared over E squared, E being the energy of the electron. And if we do this the lowest order of ME over MP, then we find that P1P3, that Lorentz inner product, is E squared times 1 minus B squared cosine squared theta. Whoops. We still have electricity then?
I don't know actually. Yes.
And we see that P1, P2 is equal to E times MP. P2, P4 is MP squared. T is P1 minus P3 squared. And this has various forms, and one of them is minus 2 p vector squared times 1 minus cosine squared theta. I'm not going to go through all of this. I think I'll just say that eventually what you get is 1/4 sum over spins of this squared amplitude is e to the 4th m proton squared over v to the 4th e squared sine to the 4th of theta over 2 times 1 minus v squared sine squared theta over 2. And so the differential scattering cross-section, so this is electrons or protons in the limit of heavy protons, is 1 over 64 pi squared. And as I said, this is essentially center of mass, and it's 1/4 then sum over spins of m squared, and this is then e to the 4th over 64 pi squared v squared p squared sine 4th theta over 2 times 1 minus v squared sine squared theta over 2. And this is a cross-section that was written down, a formula written down by Mott, and again, it holds here for energy much less than the mass of the proton. So because we took the mass of the proton to infinity, we can't have the E comparable to that. So that was Mott's formula. Now, if we go make a further approximation and say that V is small, V much less than 1, P much less than E, which is approximately the mass of the electron, and then V is P over ME. At this point, we return to the Rutherford cross-section, and we get P sigma d omega is e to the 4th and e squared over 64 pi squared p squared sine 4 theta over 2. So this is the Rutherford formula. So it is for low energy electrons scattering off infinitely massive protons. And we can take a different limit, though, if we go back to the exact formula, where this is the hard part, and then you have phase space. If you instead take the limit E goes to infinity, and you set this V equal to 1, and then P1 is E Pi, P2 is, we're still thinking of the proton as infinitely massive here, P3 equal to E prime, P final, and P4, well, it's P1 plus P2 minus P3, that's for sure. And you imagine that Pi is equal to E, Pf equal to E prime. And now if we're in the limit, we have two limits here. One is we're at high energy, but we're imagining that we're neglecting the electron mass, which is appropriate because we've got high energy. I mean, there might be several JeV electrons, so half an MeV isn't going to make any difference. In that case, we have d sigma d omega equal to e to the 4th, again, 64 pi squared, e squared sine 4 theta over 2, and then it turns out to be e prime over e cosine squared theta. And And the reason why we have E prime is that now, since the electron has very high energy, there could be some recoil on the proton. So anyway, we have cosine squared theta over 2 plus E minus E prime over M proton sine squared theta over 2. Okay. And here, ME is much less than ER. So this is high energy. So they were, at SLAC, they started out with a relatively low energy electron accelerator. I forget what it was. I don't remember what it was. Anyway, it might have been a few hundred MeV, and then it went up higher. And this was just an electron accelerator, and they were scattering electrons off hydrogen and then off other elements, I guess helium, maybe off deuterons, and then off various nuclei. And they were seeing a formula very much like this. And then they got more funding, and the electron accelerator went higher in energy. I don't know, maybe a couple of GeV, maybe 4 GeV. It's a pity I don't know these numbers, but I wasn't there at the time. Anyway, they started, when they were scattering electrons off protons, they started to see deviations from this formula. And so then they realized something was going on, and that the proton wasn't a point particle. And so it was just mysterious what was happening until they jacked up the energy yet further. And they had the energy high enough. The wavelength, the relevant wavelength of this photon, that we remember, this is the Feynman diagram. The wavelength of this photon became short enough that they could start seeing the constituents of the proton, namely the quarks. Charge constituents, because clearly the photon wasn't going to interact much with the gluon, but it would with quarks. And so what they were seeing then was this formula again, but a different value of E. And so they discovered quarks. And I think there was some confusion. The original papers where they saw the experimental information, didn't know quite what it was, but a few hundred miles south of Stanford, Galman was at Caltech, and he had been playing with SU3, and he was thinking in terms of SU3 symmetry, an SU3 symmetry that we now know is based on the fact that mu is approximately equal to md, and this is approximately equal to, but less than, ms. And these guys are much less than the scale of QCD. So the relevant energy scale, they were all like quarks compared to the energy scale. You might think of this as 300 MeV, and this is maybe 100. So he then reinterpreted his use of SU3 to an SU3 of color, and that there were quarks of charge, 2/3 for the up quark, 1/3 for the down quark, minus 1/3 for the down quark, minus 1/3 for the straight quark, and explained why they were seeing that this formula reappeared as the energy got high enough, so the wavelength was small enough, so they're actually seeing individual quarks, as opposed to the whole proton. And so that was one of the most remarkable periods of elementary particle physics. It sort of suggested to people that this was a very exciting field. And it stayed exciting until about 1982 or so. And that's when finally the W and the Z, which had been predicted by Kelman and not Kelman, Glashow and Weinberg and so forth, were discovered at mainly at the E plus E minus machine in Geneva, but confirmed at SLAC and I guess also at Fermilab. But between those experiments and the 2012 discovery of the Higgs, there was essentially nothing in high energy physics. No experimental results at all. Low energy results, namely neutrino physics, which are still going on, and then of course in astrophysics, dark energy and dark matter. Okay, my notes ended a little bit earlier than usual, so let me see. Maybe I can talk about quantum scattering for 6 minutes just on the fly.
I got a question.
Question, yes.
So you say,
Oh, Jesus, my
I can't catch that.
terrible.
Yeah. So you said Galman was
What?
So you say he was playing around with SU3. What does
Yeah.
that mean? I mean, we really used. I mean, all this is. We have a creation and annihilation fields. I see no group theory here. I mean, I don't know what you mean by when you said he played around with SU3.
Well, see, what had happened then was that people knew there were certain mesons and certain baryons. These had been discovered in experiments at Berkeley mainly, and also at, I guess, Brookhaven, and also, I guess, at SLAC. And for that matter, in Geneva. And you could put these on a, see, at this time nobody knew about quarks.
Okay.
And what was known was that isospin symmetry was almost exact in the strong interactions. And this isospin symmetry was discovered in nuclear physics, I think in the 30s maybe, and so when they discovered pions, they discovered that there was a pi plus, a pi zero, a pi minus, almost the same mass. They said this was an isospin triplet, isospin being SU2, and here you see they didn't quite know what to say because they didn't know about quarks, so they just said, well, under an SU2 transformation, an isospin transformation, you'll turn a neutron into a proton or a proton into a neutron. That was an isospin doublet. For pions, you had an isospin triplet. You had 3 of them.
Okay.
And you also had 2 doublets of K mesons. You had K0, K plus, and K0, K minus, and those were isospin 1/2
Okay.
doublets. And then there was also let's see, in the baryons you had the proton and the neutron, that was a doublet. Then there was a lambda. It was heavier than the proton, neutral was a singlet. And then there was a triplet of isospin, a sigma plus, sigma 0, sigma minus. And then was another 1/2, spin 1/2, isospin 1/2, the cascade and the cascade minus, or C and C minus. And so what you had then was, you had something like this. If you did the masses you had 8 baryons.
Okay.
All right. And what Gell-Mann noticed was that SU3 had 8-dimensional multiplets. And so did, and what about the mesons? Well, for the mesons, you had pi minus, pi 0, pi plus, and then you had, let's see, I guess you'd write it as k plus, k0, and now here I'm a little hesitant to write it down here because the masses are going up, but if I write it this way just to make it look like an 8, it looked like that. And then there was another particle, but it didn't have the mass of the pion. It was a heavier particle, but it was interpreted as the 8th meson. And so Gell-Mann pointed out that these things fitted into representations of SU3, and then when the Slack results came out, he said, well, this basic thing of SU3 would have been something like, in other words, the 3 of SU3 would have been something like UDS. Okay. And then then he interpreted this as 3 3s, and if you do 3 3s, there's an 8. I mean, there's a 27 and so forth. And you do a 3 and a 3 bar, you get a 1 and an 8. And he identified that as the 8. And then what was striking was that you had you had baryon resonances in pion-proton scattering, and one was called the delta, and it was delta plus plus, delta 0, and delta minus. Then there were some sigma stars like this, and then there was the cascade star, and then no one had seen anything here. And these were evenly spaced in mass. And he said, aha, this is the 15 of SU3. And he predicted that there was an omega minus up there around 1670 MeV or so. And then they looked for it, I think at Brookhaven, and found it. And people thought, my God, he's a genius. Well, he is. Yeah. Well, it still is. Yeah. And so people went nuts about those things. And of course, this was before Xerox. Well, there were Xerox machines, but there wasn't any internet. And Gell-Mann's father ran a language school in New York, and so Gell-Mann has always been very sensitive to language. So he doesn't just dash off paper with, without worrying about the words and the organization and so forth. And so he was always a little slow to publish. And so people not at Caltech were all sort of confused. What are they doing out there? Anyway, well, I'll do Compton scattering on any other questions? All right, let's